Rather contentious issue in economic theory in general and in game theory in particular, that of the concept of the Homo-economicus agent, the all-knowing, perfectly intelligent economic human being. So for outside economics, the Homo-economicus being is sort of a villainous character, very ruthless, self-preserving, and so on. But for in economics, at least in neoclassical economics, people consider Homo economicus as the being to be idealized, or that's the perfect being. So in this talk, what I'm going to do is to critically analyze this concept of Homo economicus, precisely where does it come from, and what are the underlying assumptions, and hopefully I will show that the way it is presented in the standard theory is in no way unique, that there is a perfectly possible alternate view one can take, which perhaps will make Homo economicus less of an evil. So let's see. So the concept of this optimizing a person, Homo economicus, has its roots in the concepts of game theory, actually, especially non-cooperative game theory. So in fact, at the start of, so for example, in 1950s and so on, when Morgenstern and John von Neumann wrote their games and economic behavior, they envisaged that game theory will be useful to economics as calculus to physics. So a prophecy actually which came to be true, so well attested by the fact that no less than about 11 game theorists have won a Nobel Memorial Prize in economics. Okay. So that's no surprise, because in economics, at least in a very fundamental way of looking at microeconomics, for example, it's all about strategic interactions between agents that give rise to the microscopic picture, and you have a lot of such microscopic stuff to make the macroeconomics. So that's a very, what is that? So I'm pushing a lot of things under the carpet there, but that's kind of a view one would like to take, especially for one who trained in statistical physics. So we are going to look at this microeconomic picture in detail. Okay. So as I said, it comes from the theory of games. They describe the strategic interaction between agents. And if you want to describe some strategic interaction situation quantitatively, a social interaction or an economic interaction, so the quantitative components are these. So you have a set of players, usually called as agents, and then you have rules which define possible actions an agent can take. Okay. And there are payoffs. So payoffs basically are the payouts, and that depends upon the action of both self and others. So that is the strategic component, and the basic so the payoff is assumed that it will reflect all the preferences an agent has, whatever preferences he has. So we'll come back to that a little bit later. But having this, having such a structure, then so the assumption is that an agent tries to maximize her payoff. That's what an agent would like to do, because the payoff reflects, as I said, all the preferences an agent has. So the question, the basic question is this: that so what should a player do to do this, to optimize or maximize her payoff? So that's it's a very non-trivial optimization problem, because of this particular fact that so the payoff of an agent depends not only on his action but that of others. So this is actually a very crucial difference between, for example, physical interactions and economic or strategic interactions. So yesterday there was a talk by Professor Jain. So he mentioned that the interactions we usually consider in physics is different from that in economics in the way that the economic preferences can change over time and so on. But there is a more fundamental difference, as you can see from here, that so this is an interdependent decision problem. Okay, so in physics, for example, you can describe the behavior of a system by a single function like free energy or entropy, and the principle the system will follow is optimizing this function, maximizing entropy or minimizing free energy. So this is completely different. You have a couple of agents, they have their own payoff functions, and they would like to maximize their individual ones. Okay, so one of the basic assumptions, as I told earlier, is that, so let's look at this question a little bit more in detail. Okay, so there is this assumption of self-interested agents in games and economics. So perhaps it's best epitomized in these words of Adam Smith, that it's not from the benevolence of the butcher, brewer, or the baker that we expect our dinner, but from their regard to their own interest. So meaning that the agents are self-interested. Again, so how exactly this taking care of own interest is incorporated in strategic interactions? So there are two components to this. The first is, as I said, the agent preferences are accommodated in payoffs. Okay. So that's the first part. Now this is often a source of confusion when we say that the economic agents need to be selfish and so on. So as far as the underlying game theory is concerned, it's perfectly capable of handling altruistic agents or non-selfish agents or whatever, because so it can perfectly handle a brewer who just, or a so somebody who can give stuff for free. Okay, so that's not the point I'm going to talk about. A more fundamental question is taking care of this interdependent optimization problem. That's what. So the formal name for such a stuff is what is the solution concept you use to solve a game. Okay. So as I said, the baker can be perfectly reasonable if he gives bread for free, and that's what gives him the highest payoff. That's only one part of the question. So we are concerned about the second part, that how do they take care of their own interest with regard to their interdependent optimization problem? How do they maximize their payoff? So the standard concept is that you do this, that maximize your payoff assuming others' actions fixed. Okay. So if every agent does that, then you have what is called as Nash Equilibrium. It's basically a strategy selection by each agent where no one agent has any incentive to deviate from it. So if you know the game of prisoner's dilemma, the argument is that defection, no matter what my opponent does, my best response is defection, and hence I will defect. So that's what Nash optimization will tell you to do. Okay. So needless to say, that's a very general and appealing concept, optimization concept, because Nash himself proved that such equilibria exist for all games with a finite number of players and a finite number of strategies. So that's those two lines basically summarize his PhD thesis. Okay, and so it'll be I can't do justice to the fact that how influential that concept was in the remaining years. Perhaps again well illustrated by the fact that he himself won the Nobel Prize in economics many years later. So ever since its introduction, it's sort of an adage that maximizing individual good, agents maximizing individual good will or should play Nash optimization strategies, will or should, depending upon whether you want to take a normative viewpoint or a descriptive viewpoint. Okay. So that's what the according to the Nash optimized, that's what the ideal agents should do. Now that has obviously led to a lot of problems. So what are the problems with the Nash strategies? So there are two problems. One is at the conceptual level. So the conceptual level problems are often called as dilemmas in games. So the dilemmas in games is basically that the Nash strategies, if agents actually follow, will lead to suboptimal outcomes. For example, in prisoner's dilemma. So social dilemmas in general illustrate that point very well. And okay. So a more from a practical point of view, a problem is that experiments reveal that real life agents don't often follow Nash strategies. So they fail to play these optimization strategies. But that one can explain away with a number of arguments. For example, one can say that, look, okay, we have some experiments or observations, but they don't correspond to the assumptions made, assumptions behind the Nash. One usual way it is done is that one would say that the actual payoff that's the agent perceive is different from what you think, and actually they are playing Nash strategies, but that of this modified game they perceive. So the conclusion, in some sense, is that real life agents are kind of stupid. But then that's a problem because real life agents often gets much more payoff than the ideal game theorists do. For example, in prisoner's dilemma, you observe cooperation in a lot of instances. Okay, so this is why for example, Amartya Sen famously called these rational agents as rational fools because they optimize their payoff just to be behind the ordinary agents who gets much higher payoff. Okay, so if you look into these problems, so one can realize that all of this comes from the optimization principle that they follow. Okay, so agents optimize assuming others' action fixed, and if you look a little bit more carefully, you can see that in the Nash way of optimization, so an agent actually looks only at the payoff structure of a game and not necessarily how the other agents is going to decide upon what actions he will take. Okay, so for example, in PD, if you are a Nash optimizer, you will just play defection, no matter you don't think about what the other agents are thinking and so on. So the question we were asking is, so are there alternative viewpoints one can take about this problem? Okay, so and I will show that it's certainly possible. So for example, so if you consider symmetric game situations, so let's look at the symmetric game situations. So for symmetric game situations, one can take, for example, this view that in a symmetric game situation, agents realizes that they are actually facing a symmetric payoff structure, and also they are also realize that they are equally capable in analyzing the situation. Okay, so these two should lead to the logical conclusion that so whatever their thinking process is, in the end, they will be taking the same action. Okay, or as we said, their propensity for a given action must be the same. So this is the coaction concept, and it's important to note that here symmetry operates at two different levels. So one is at the payoff structure level. Okay, that's given by the payoff structure, it's completely symmetric. And the other is among the agents. An agent consider the other as symmetric as him, in the sense that he has the same capabilities as me in analyzing the situation and so on. So later on, I will tell you how, for example, such a view can be accommodated in a descriptive view of the same equilibrium, but right now that's a theoretical construct. Okay, and agents realize and consider this when making their decision. Okay, so that's the essence of coaction concept, and so the rest. So I will show you how, for example, that changes the standard results and how one can generalize this to consider even non-symmetric and other situations as well. So that's the crucial difference. And if you want to take a very hardliner viewpoint, then one can say that the assumptions in the Nash theory that both agents are equally capable of analyzing a situation, and but still they can unilaterally deviate from their strategy. They are kind of they don't match with each other. Okay. So if you understand this particular slide, then that's it. That's the talk. The rest is kind of showing its consequences and its importance. Okay. So it's important to note that I'm not saying anything like agents are not selfish and so on and so forth. So the agents are selfish. They are selfish, and they are self-optimizing agents. They still want to maximize their payoff. So the coaction, as I presented, it's not like something comes from the trust or something like that, and it's also independent of any particular definition of intelligence you assign to agents. So the argument is that if the same, whatever your definition of rationality or intelligence of agents, as far as the same definition applies to all the agents, the coaction principle should go through. So that's the argument. Okay. So let's see how this works out for a two-person game. That's the simplest game one can think of. So of course you can represent a two-person symmetric game by such a payoff matrix. So you have agent A and agent B. Both have two actions available to them, action 1 and action 2. And there are a set of payoffs, usually denoted by reward, sucker's payoff, temptation, and punishment. That's the generic payoff matrix of a 2x2 game. And depending upon the hierarchy between these four parameters, you have various games like prisoner's dilemma, chicken, stag hunt, and so on. So let's look at so given this kind of a structure, so what do a coaction optimizer will do? So he'll do the following. So this is the coaction payoff function that they would like to optimize. So it's an agent expected payoff, assuming that the other agent will take an action with the same probability, which is P here. So you can see that it's just a simple quadratic function in P. Okay. So maximize W with respect to P in the interval 0, 1 gives you the optimum coaction strategy. So let's call it P star. Now it could be that the maximum, the value of P which maximizes that function is at the boundary or at 0 or 1. It could also be well in the middle. If it is in the middle, then middle mean in between 0 and 1, then it's given by this. So that's just maximizing that simple function with respect to P. Okay, so let's look at some of the simple games, like for example, prisoner's dilemma. Prisoner's dilemma has this structure with this particular hierarchy between the payoffs. Temptation is larger than reward, larger than punishment, larger than sucker's payoff. So what you can prove easily that so the coaction solution is the following, that as far as the temptation is low enough, okay, that particular value, then agents will fully cooperate. Okay. And when T is greater than 2R, they resort to a probabilistic strategy given by that. So you can see that even if the temptation is too large, for example, T goes to infinity, the minimum amount of cooperation that the agents will achieve is half. Okay. So no dilemma for prisoners in that. So you can take it as a solution of the dilemma of the prisoners. So even in one short PD game, cooperation emerges as a rational outcome. Okay. So what about some other important game like hawk-dove game? So this is again a well-studied game, goes by the name of game of chicken, hawk-dove, or snowdrift in different areas. So here the worst possible outcome is when both play defect. Both play hawk, they attack each other and annihilate each other in some sense. That's the worst possible action one can take. Mutual aggression gives you the worst payoff. Okay? And that's reflected in this hierarchy where the temptation greater than reward greater than. So the last two are interchanged compared to the prisoner's dilemma game. So it's often studied in evolutionary biology a lot. and has a lot of significance there. So what is the Nash equilibrium of this game? So in this case, there are two pure strategy Nash equilibrium. So this is an example payoff. So you can, so what is marked in blue are the Nash equilibria, for example. So one equilibrium is if agent A is aggressive, then it's better for agent B to be docile, and likewise, if agent A is docile, then, if agent B is aggressive, then it's better for agent A to be docile. There is also a mixed strategy Nash equilibrium in this case, given by that. And you can see that if temptation is too high, then the mixed strategy Nash equilibrium tells you that you should always play aggressive. Okay. So what about the coaction solution? So one can work out that the coaction solution is again this, that for the temptation is low enough, then you play docile, you play dove. And if it is high enough, then again you play a mixed strategy given by that number. So it's interesting to note that when the stake is high, the coaction gives you, again, P star goes to half, play docile hawk with probability half, with the corresponding payoff given by that W star, which is 1/4 of the temptation payoff. So it's interesting to compare this with, for example, the corresponding mixed strategy, Nash equilibrium, which is also an evolutionary stable strategy. And you can see that the Nash strategy, when the temptation is too high, results in mutual aggression and basically mutual annihilation. So the coaction basically gives you much nicer strategies compared to Nash, but that's not the aim. So sometimes it's better to take a dynamic picture of Nash equilibrium and the coaction equilibrium. So what has been done here is to So this, for example, is the P1 is the probability that with which agent 1 will cooperate, and P2 is the probability that with which agent 2 will cooperate. And what has been shown here is that if you randomly start from some combination of P1 and P2, and if they follow Nash kind of optimization, what is their final state will be. So you can see that this is very standard, that it leads to mutual defection in the case of Nash optimization. But look at the coaction optimization for these values of parameters. So it actually leads, the coaction leads to that equilibrium, which I just described earlier. But so the thing from this dynamic picture is that that equilibrium is stable with respect to coaction optimization. Okay. So that's a two-player situation. So how do we, or can we generalize this into many players and iterative situations? Well, indeed, we can. So note that the key point is this, that how to define the symmetry between the agents. So of course, all players need not be in a symmetric situation in these kind of games. So the important question to answer, to address is how the agents infer symmetry in a game situation. So there can be several ways to model this. For example, one can take the view that in an iterative situation, one can infer symmetry based on the choice of action of agents in the previous round, for example. Because if you have committed the same action in the last round, then that can be taken as a cue that you are facing a symmetric agent. So what happens when that symmetry is not there? Well, there are many possibilities here, so I'll tell you that later. But so one can, for example, simply take the view that if there is no symmetry, then agents actually use Nash optimization in non-symmetric situations. Okay. So, but this need not be the case. For example, viewed in this way, Nash optimization and coaction corresponds to two extremes of considerations. For example, in one end, you have the Nash optimization, where you optimize, saying that I fix the strategy of my opponent. And on the other spectrum, we have the coaction concept, which says that both of us will have the same propensity to play a strategy. And of course, you can consider a gradation of things between them. For example, you can consider a linear combination of Nash way of playing and a coaction way of playing, parameterized by, let's say, one parameter. Okay. So let's take for the moment this view that if there is no symmetry, then agents use Nash optimization. Okay. So again, one can work out the details. So it's like, you know, so basically, if you have an iterated PD between two players, okay. So basically, it says that whenever you have committed the same action in the last round, then you use a coaction optimization, and when you use different actions in the last round, then you use a Nash way of optimization, and that one can show that will lead to a win-stay-lose shift kind of strategy, a well-known strategy in prisoner's dilemma game. What happens if you have many players? So that's a very interesting situation, because what we studied in this paper is also an instance of a public goods game. So where one can take, one can either cooperate or defect with n-1 players. So this is, note that this is not individual interaction between n players. So if I'm a cooperator, I cooperate with all the remaining players. Okay. So what one can show in that is that coaction equilibrium corresponds to a majority of cooperators coexisting with minority defectors. So how do one do that? So basically, if you have n-player iterated PD, then you have the situation that in the last round, a group of players might have cooperated and another group might have defected. So those are the two possible actions. And what you do is that you consider all those cooperated in the last group as symmetric. So they are a group in which there are a lot of players, but the propensity for them, all of them, to take a particular action is the same. They don't say it's not necessary that they will take the same action, because, for example, if you have 5 players are cooperated in the last step, then the probability that all of them will cooperate again is p to the power 5. Okay. It's not. And then you have 2 groups, and you consider what is the Nash equilibrium between these 2 groups. So that is worked out in the standard way of best response. Okay. So the idea of the coaction actually originated in this paper when we analyzed minority games. So I won't talk about this in detail, but so the only point I will make is that at least some of you know that the minority game when introduced. So one of the motivation was to model boundedly rational behavior. So if you look back at the original paper, the El-Farol bar problem, then you will say that you will see statements like the minority game actually essentially demands that agents should play in an inductive way, not like a game theoretic way. And so what we did in this paper is to show that that's not actually correct. Actually, the intelligent self-optimizing agent actually can do much better in a minority game. Okay. So as I said, if you simply take multi-agent situations from a conventional game theorist point of view, then actually defines a very novel class of strategic interactions. As I said, you have players, but now players are a group of agents who independently selects the same action. Okay, so that's it as a normative concept. So does this principle has anything to do with real life? So it turns out that it has. So as I said, realizing symmetry is the crucial part in the coaction framework. So one can argue that it's most likely to be realized among members of a given community. So it's a question of inferring symmetry. How do one person infer that somebody is kind of same as him? So in this context, one can use the word similar. So it could be based on cultural, it could be based on external attributes, money, something else, I don't know. So there are a host of possibilities there. For example, so if I'm talking about experiments in PD, for example, so it has been observed that things like cheap talk or social projection. So cheap talk is a word basically denotes that you allow the players who are going to play the PD to interact with each other before the game and so on. So one can view these results in the light that these are possible mechanisms which allow the players to affirm a shared set of values. Okay? So we are kind of in a similar boat or something like that. So another stuff in biology is tag-based cooperation. So all of this is somewhat similar in the sense that it's a question of how do you identify somebody else as belonging to your group. For example, so this is just a recent paper which actually argues that there is actually genes operating at that level. Now it's interesting to note that there are actually works by famous people like Rubinstein who actually test our assumption or something very similar. So what he does in this paper is to analyze a PD kind of situation and say how often the agents actually employ a coaction-like thinking in the sense that others, so that captures that. They do what I do. So depending upon the situation, you can see that you can take the coaction as either a descriptive principle or a normative principle. For example, I can as well start from such kind of a work and argue that coaction is the right kind of mathematical principle behind that kind of reasoning. So the question when we introduced this concept was that, okay, if that is so simple, then why didn't anybody else think about it? Okay, that's a valid question, and we have spent actually hours and hours searching for similar concepts in all sorts of areas, and it happens that there are actually not many works which actually tries to tweak the optimization of agents in this way, that you still preserve the self-interesting part and you still preserve all the basic assumptions of game theory, and then tries to propose an optimization principle. But there are, of course, similar arguments appeared. For example, if you read this, this is one of the famous texts by Rappaport, Twoperson game theory, and towards the end you will see that something like this. Because of the symmetry of the game, he's talking about PD here, rational players will choose the same action, and as it involves a higher payoff, they will always opt for mutual cooperation. Now then he immediately goes on to the conventional argument and says that how can that be true, and that's kind of involved in a philosophical musing. So somewhat similar idea has been independently put forward by Douglas Hofstadter in the context of an n-person PD. So essentially he talks about hyper-rationality and so on and so forth, but again in the context of PD. Now it turns out that there is actually a very similar concept proposed by a famous economist, American economist, John Roemer, called as the Kantian optimization. Now he, however, takes the view that the optimization actually has this kind of a background. He motivates this by saying that agents involve in some kind of Kantian thinking, in that one should take those actions and only those actions that one would advocate always take as well. So he introduced this in the context of production economics. Basically what he is saying is that a company will producing something and it's in competition with something. So he's asking the question, suppose I increase my production by a factor alpha. So in the Kantian way of thinking, it's like this, that okay, I want to increase my production by a factor alpha, but I ask myself the question, what if all others do the same thing? Am I comfortable in that situation? And if the answer is not, then that particular state is a Kantian equilibrium. So it turns out that, surprisingly, or maybe not so surprisingly, in the prisoner's dilemma game, the Kantian optimization gives the same answer as the coaction optimization, except that Kantian optimization has this extra caveat that mutual defection is also a Kantian equilibrium, but he explains that as a trivial Kantian equilibrium. This concept itself is somewhat related to another concept called as conjectural variation optimization. So here the idea is that an agent has some kind of an idea of if I change my strategy, how others will change their own. So basically, you have a equation for, they have a conjecture for dp1 by dp2, partial derivative of p1 with respect to partial derivative of p2 in the context of 2% games. So it's kind of reassuring to see these works because so John Roemer is much more respectable than me, perhaps. So what is the summary? Summary and conclusion. So the coaction optimization take into account the rationality of all agents in a strategic interaction, and as I show, will lead to completely different results. So these are some things I already told. The social dilemmas resolved, and rational selfish agents can produce socially optimal state, even in non-cooperative situations. Okay. So thank you, and here are some of the references.
Thank you, Dr. Sasidevan, for such a thought-provoking talk. Any question from audience? This concept of coaction that you're talking about.
Yep.
If you consider just an iterated version of it, wouldn't like what they call evolutionary game theory, wouldn't that kind of give this, if you want to consider the first iteration of it?
So you're saying that they will just start off with mutual cooperation or something?
Start off with mutual cooperation there.
Yeah. So usually in that setting, what we consider is that so there are several ways to explain this. One is to say that in the first step they don't know how to behave. Now, having achieved mutual cooperation, what is the further evolution of the system? So it's usually assumed that there is some noise, which occasionally makes an agent to defect, or may not be defect, but interpret that as defection by the other agent. So it could arise from, for example, a lack of communication, noise in the communication channel, and so on. So that's a kind of standard way it is modeled in.
You say from there, then it automatically goes down back to the Nash equilibrium.
No, so from a state like mutual defection, it will go to mutual cooperation.
Okay, so I have a very basic question. How Homo-economicus differs from Homo sapiens?
Homo sapiens?
See, in your title you said.
So I said, yeah. So I said, so there is this all sorts of confusion when you say Homo economicus. What do we mean by rationality and so on? So in this setting, it's very easy to define rationality. It's the optimization principle that they use. Now, so what is Homo economicus? Okay.
Homo sapiens.
It means. Okay, it's a bit hard to define. Self-interested agents, but again, what do you mean by self-interest? Economists will say that it's just economic self-interest, economic welfare, but sociologists will say that no, there are psychological factors involved, like the pleasure or warm glow of feeling or something like that. And so Homo sapiens differ from Homo economicus in these aspects in economics, but from a game theoretic point of view, I don't think. Do you need a distinction at all? I'm not sure.
No, but another way of thinking of this could be that whereas if you look at it from the Nash perspective, you would say that Homo economicus is very different from Homo sapiens because Homo sapiens tend to cooperate a lot, whereas they shouldn't, according to Nash point of view. Whereas coaction is showing that there's actually no difference.
Yeah, so that's what I said in the beginning. So the Homo economicus, as self-interest optimizers, is as not as bad a concept as it made out to be. So they're more related to Homo sapiens than the conventional.
Thank you. So thanks to the speakers once again.